Right, well, welcome back. I hope you've returned from lunch suitably refreshed and also suitably warmed. We are aware of the rather icy nature of this room, and over lunch, Annette told me a rather interesting anecdote, that actually in the Meitner papers here, there are letters from Otto Frisch to Lise Meitner complaining about Britain and how it's cold and how we haven't mastered heating. So some things don't change. You may, if you look carefully, you can see that some cunningly concealed radiators have appeared and been hidden around this hall over the lunch break. We hope that the heat will rise with our discussion during the afternoon. But without further ado, let me hand over to Dame Athene, Master and Physicist, to discuss the scientific and political legacy of Lise Meitner.
Thank you very much, Alan. I hope people would agree with me. We got off to a flying start this morning, fantastic session, and I'm very much looking forward to this next one, as Alan says, about the scientific and political legacy of Lise Meitner. So we want to look at the legacy, both in terms of the science that she so passionately loved, her role as a pioneering female scientist and as an exile. I mean, it has become very clear there are all these different strands to her life. And yes, maybe she wanted to be remembered simply as a physicist, but for the generations living now, we can't forget these other strands which so much coloured her life. And now, it would be fantastic to think that exclusion on the grounds of gender and race is a thing of history, and that the challenges she faced and overcame are no longer relevant to her successes today. But I think everyone in this room will know that that, sadly, is not the case. And I'm sure some of our speakers will be making this point forcefully. I know enough from my own life to know these obstacles still exist. And talking to early career researchers, and Jess Wade, I don't know if is Jess here yet? Jess is right at the back. Jess, who will be talking in the final session, some of you may know, has been taking it upon her to write up the life stories of female scientists on Wikipedia. I think it's at least one a day. It's an amazing thing to undertake, and it's really making a difference to the way women scientists are represented in what is usually seen as sort of the place that people go to as a first place to find out anything. So I'm afraid that by and large, lazy stereotyping and outright bias is still alive today in our labs, and we need to recognise that times haven't changed as much as we would like. Now, to talk about this further, you can see I am joined by four eminent researchers. We have two physicists, and we'll start off with the science, starting off with Val Gibson, who is a fellow physicist in the Cavendish here in Cambridge. And she tells me she'll be talking about the physics at a nice low level that is comprehensible to everyone in the room. And then Heinz-Eberhard Mahnke will talk, I think, more specifically about some of the heavy elements and issues that were very close to Lise Meitner's heart. And then we'll move on to talk about her legacy in other aspects with the science writers Georgina, Ferry, and Tanja Traxler. And what I've discussed with them, what I think we'll do is, rather than, as we did in the morning session, with questions to each speaker after each individual talk, we'll take the two physicists' talk as a pair, and then have questions to them, and then take the two science writers' talks together, and then, depending on timing, open it up more generally to the whole panel. So, over to you, Val.
So thank you very much, Athene, and thank you very much for inviting me to this symposium. It's a very different audience to the audience I'm used to, and the gender balance is quite good here. I'm used to talking to mostly men and maybe one or two women in the audience. So it's refreshing, let's put it that way. As I said, I'm not a historian, I'm a physicist, and I'm a woman physicist, and I'm very proud of being a woman physicist. but I'm not so proud of the fact that there are only 2 women professors in the Cavendish laboratory here, and they're both on this stage. And that just shows you, with the number of women that we do have in the Cavendish laboratory, that there's still changes to be made, although it is changing quite considerably, and quite considerably over recent years. Now, I've also got a web page, thank you, Jess, for my web page, and I'm also proud that a Nobel Prize winner who was a man actually put my photograph on the web page as well. So I've even achieved a Nobel Prize winner working for me. So that's good. So I've admired Lise Meitner for many years, and I've given lectures on nuclear physics, particle physics, quantum physics to all of our undergraduates. And actually, I'm ashamed because I didn't mention her name when I was giving the lectures, and I wish I had done now, but then I didn't mention anybody else's names either. I just concentrated on the science rather than the people involved. That may change in the future when I give lectures then to include people involved in the work behind it. So I'd like to just take you, first of all, from the beginning of the 20th century physics, and here Graham actually described this very well and very succinctly in words. Of course, being a scientist, I can't do words very well. I have to have diagrams. And here's a picture of the atom as we know it from Rutherford's time. And, of course, let's try and change this. The electrons, which are the things that go around, the atomic nucleus, was discovered by J.J. Thomson in the Cavendish here in 1897. So we're very proud of that discovery and its associated Nobel Prize. And then also the work of Rutherford when he was at McGill and also in Manchester and Cambridge, who discovered the atomic nucleus. So we know that we've got this very hard blob in the middle of atoms, which is the atomic nucleus. And the size of an atom is 10 to the minus 10 meters approximately. So that's our picture of the atom. We now know that the nucleus is made of the protons and neutrons, and you have to think about the energies involved to try and probe down inside the nucleus, because you have to go down 10,000 orders of magnitude in order to try and find that nucleus and indeed the proton and neutron inside it. And the neutron was discovered by James Chadwick here in 1932. And he's famously said that if circumstances had been slightly different, then he would have expected Lise Meitner to actually have discovered the neutron. So it really is, she was very high in his estimations at the time when he discovered the neutron. And there's a nice program, if you like, if anybody watches in our time, about the neutron, where I took down to Melvin Bragg, I took down Chadwick's sort of vessel for producing neutrons, and he was so bemused by this, he thought it was a little train engine or something and did not understand at all what the science was about. So it's a nice little podcast, me trying to explain to him about the discovery of the neutron. Of course, Lise is very much, in my estimation, the founder of nuclear physics. And we've heard already today all the great science that she did on fission, explaining it with a liquid drop model. And I cannot tell you the number of exam questions I have set on the liquid drop model. And every student that comes out of Cambridge will tell you every term that goes into the liquid drop model and how important it is in their undergraduate research. And then there's all the other things that she did as well that I wasn't so familiar with, but now I don't know why the Auger effect is called the Auger effect. It should be called the Meitner effect, really. I just don't understand that. Anyway, she was the founder of nuclear physics. And also, one thing I'm very proud of is the fact, the very special relationship that she had with Otto Robert Frisch, because he was appointed the first head of nuclear physics in the Cavendish laboratory. And really, he actually started the science area in Cambridge that I'm involved with now. And he's very famous for actually producing and building what we call sweepnik, which was a mechanism for actually tracing the tracks in bubble chamber pictures. And we still have, in the Cavendish, we still have the table that Sweepnik was used. And I'm also very proud of the fact that I'm the 5th head of high energy physics at the Cavendish laboratory, so I guess I'm sort of the great-great-granddaughter of research of Otto Frisch, and maybe a little bit of Lise Meitner in there as far as the research is concerned. So he really, he started my field in the Cavendish laboratory. So where have we gone in the last 80 years since Lise discovered nuclear fission, and the neutron was discovered as well? Well, we've gone one step further inside the proton and neutron. We now know that the protons and neutrons are made of quarks, and as far as we know, they are the most fundamental matter particles that exist. So everything that you see around you, everything that we make in collider experiments, say at CERN at the Large Hadron Collider, are made of quarks. And the neutron is made of an up quark and 2 down quarks, and the proton is made of 2 up quarks and a down quark. And you can pair up the quarks, or you can put them in triplets to make all the other particles that have ever been discovered since Lise's time. So we now have this picture of everything that we know about particle physics, and we put it together in what we call the standard model. And as you can see on the left-hand side here are the quarks. So there's the up and down quarks of the protons and neutrons, but also there are 2 other families, and the up quark and the down quark have sisters called the charm, the strange, the top and the bottom quark. They are all heavier, they've got higher masses. And then we've got the electron, which is the atomic electron, and the electron also has 2 sisters, the muon and the tauon as well. And also, in order to explain radioactive decay, we also need neutrinos, and we've got 3 neutrinos of the 3 types as well. On the right-hand side, within the standard model of particle physics, we have the force-carrying particles, the photon, which is the carrier behind electromagnetism and light, the gluon, which keeps the atomic nucleus stuck together inside the atom, and then we have the W and Z bosons, which are the carriers of the weak force. So they're responsible for radioactive decay, if you like, and various types of radioactive decay. Keep the sun shining and so on. And then sitting behind this is this illustrious Higgs boson, which was discovered in 2012. And the Higgs boson is the thing that gives all the other particles their mass. And I could give you many lectures on the Higgs boson, but I don't have time to do it here today. So the Higgs boson, that's probably the last thing that you heard in the papers was being discovered at CERN. And I just want to tell you where we are now and what the problems are we have currently at CERN and in the field of particle physics. So other things have been discovered. First of all, we found new not new particles, but new decay modes of the Higgs boson. These were expected, but are very, very difficult to observe. And that hit the press recently. So we found a Higgs boson going to 2 bottom quarks. We've also discovered what this headline is, the doubly heavy particle which shines light on the strong force. Basically what that is something that looks like a proton or neutron, but instead of having an up quark and 2 down quarks, we have an up quark and 2 charm quarks. And so it's got a lot of charge associated with it, and it has particular interactions which are different to the proton and neutron because it is charged compared to the neutron. So we've discovered that, and we've also discovered pentaquarks and tetraquarks. So we've discovered things that were predicted in the 1960s, actually, by Murray Gell-Mann, who said that quarks can come together in pairs, or quarks and antiquarks coming together in pairs, or in threesomes. He also predicted they should come together in 4s and 5somes. And now we've discovered these at the Large Hadron Collider. So there's lots of discovery going on. The one problem with the discoveries is what we call beyond the standard model. And here I just summarize a few of the questions that are still open to us. One is that the standard model is an approximate theory. It's based on very good theory, but it's only approximate. And if you look at the Higgs boson, it has a mass which is actually 125 times the proton mass, but it's very unnatural within this theory. It just doesn't sit very well in the calculations in order to really understand what the mass should be. Also, it's been discovered that neutrinos have mass, and their mass is unexplained. It's not contained within our standard model at all. We don't understand why they have mass. There's too many free parameters in this theory. And, ideally, if you've got a theory, you want 0, 1 parameter, just one number that you have to put in there. This has got a huge number, 25 free parameters. And there's no unification of the 4 forces. I've told you about the 3 forces which go into the standard model, but Einstein died trying to combine gravity with electromagnetism, and people are still trying to do that today, is trying to include gravity within the theory, so we can explain all of the 4 forces of nature. And then, minor problem, we only know about 4% of the galaxy, our own universe that we live in. All the rest is contained within dark matter, 25% dark matter, and also dark energy. 70-odd% of the universe is made of dark energy. We do not understand why. And also, we live in a universe made of matter and not antimatter. If you take Einstein's E = mc squared, you would believe at the beginning of the universe that matter and antimatter were created in equal amounts. But we actually live in a universe made of matter. We don't understand these questions, and we're really trying and find out at least some of the answers of these questions. But I'm pretty convinced that one person who would be very interested in these current questions in science, and who potentially could actually have had some of the answers to these questions, was Lise herself. I'm sure she would be thrilled by the situation as it currently is. Thank you.
Thank you very much, Val, for that introduction to the topic. And now I think we'll get more on the heavier atoms. Over to you.
Okay, here we are. First of all, thank you, Dame Athena, making the connection between the Churchill archives and myself. And then I thank Alan to actually get into closer contact with me and vice versa, and that he arranged such a nice symposium, and that I'm actually here on the panel and can talk about that. My connection to Lise Meitner, I guess, will become a little bit clearer further on. So, first of all, I want to stress the physics behind what she was doing, what kind of topics were her topics, so to speak, and what turned out of her topics nowadays. And that is, of course, in my opinion, it relates to the beta decay. And as a synonym for that, the neutrino discovery, etc., and what's going on with neutrino physics nowadays. And then Val mentioned already O.J. Meitner effect. I will mention that a little bit further. And then, of course, the other research topic, the trans-uranium elements, or the nowadays called super heavy elements. What have we achieved there? Going back here, this picture, this photograph, actually was taken in Bonn on a lecture. I like this photograph very much because it shows the fluorine 19, and it shows the beginning of writing down a nuclear reaction. One of the very first experiments done at our institute, which I explain a little bit later, the Hahn-Meitner Institute in Berlin, uses a fluorine 19 reaction. So I like this photograph very much. Okay, a few words about the beta decay. Beta decay is a radioactivity where one nucleus A transforms into a different species, into a different element, nucleus B, and emits an electron. And for a long time, these electrons were considered, were measured, were found to result, to give a continuous energy spectrum, which was absolutely not understandable at that time, because what was expected in such a decay was something to give a line at a certain decay energy. And there was no line. Although there were lines in the spectra measured, and the relationship between what is what, lines and continuous, that was the topic of research for many, many years in the 20s. Anyhow, and here comes the close relation, and that there was no distinction between theorists and experimentalists. They were working close together. Lise Meitner came to Berlin to join Max Planck as a theorist. So but she liked to do experiments as well. So the separation and distinction between theoretical physics and experimental physics was not there at that time. Another thing is that physics at that time was just atomic and nuclear physics. There was no distinction made between solid-state physics, surface physics, or what have you. It was physics. It was the top issue in physics was atomic and nuclear and elementary particle physics. That's the division we nowadays do. So the theoretical physicist who entered this problem about the observation of the continuous energy spectrum was Pauli. He introduced the new particle, which took a long time to actually experimentally be proven, and that's the neutrino. And he wrote a letter, and he put, I translate, "Dear radioactive ladies and gentlemen." And it was basically addressed to Lise Meitner, because it was an open letter, but it was given to Lise Meitner. So here in this letter, he explains that one needs the introduction of a new particle which has not been identified yet. It took more like 30 years until it finally was really proven that such a particle exists. But so that was Wolfgang Pauli. Going back from the particle which was introduced as a neutrino, he named it Neutron at that time, but later it was then changed into neutrino, developed a whole branch of physics, namely neutrino physics, as part of particle physics, astrophysics, cosmology, and here comes the term which we heard already about cosmetic physics, not cosmetic rays, cosmetic physics. That was the announcement of the seminar talk she was giving when she was given the habilitation. And journalists made out of the cosmic physics or cosmology, they made out of that the cosmetic physics. And I will then also switch over to surface science. You will see why. Neutrino physics. We heard about the mass of the neutrino. But it's known, it's proven that the neutrino has a mass, and these various species, these various families, electron neutrinos, tau neutrinos, mu neutrinos, they have different masses. The exact figure of the mass, the exact value of the mass is not known, not even for the electron neutrino. And for that, one has set up a many different experiments were set up over the years. The most recent one is taking place at Karlsruhe, Karlsruhe Institute of Technology, and it's named Kathrin Karlsruhe Tritium Neutrino Experiment. It is such a heavy instrument, which was shipped on the Donau, and it had to be carried away on trucks and lorries. So here you see that they just managed to come through these housings to make the transport of this vessel. There's a source, the tritium source. The tritium emits electrons. The maximum energy is 18,000 electron volts, 18 keV, and one is looking for differences here at the very end. Here's the difference when there is a difference in one of a rest mass for the neutrino of 1 electron volt. It shows up here as a slight difference here at the end. That's what they want to look for. There's a solenoid as a detector and the complicated transport of the electrons which are emitted from the source. But not only the mass is of interest, it's also where the neutrinos are coming from. It's not only that one wants to understand the standard model and what is beyond the standard model, but also what's going on in the whole universe. And that is using the neutrino as a kind of a messenger. And for that purpose, there's an experiment set up in the Antarctic ice in the order of something like more than 1.5 kilometer deep, and a field of something like 100 by 100 square meters size in the lateral direction. And here you see a chain of detectors hanging down the more than 1 kilometer. And when there is a neutrino reaction producing a muon, that muon is detected here by these detectors in the ice of the Antarctic. And this is only one experiment. There are other experiments in the Baikal Sea, and also they want to set up a new experiment in the Mediterranean Sea as well. So you see a lot of effort is taken to understand what's going on in the universe and to use neutrinos for that. These funny particles which were just missing in the experiments when Lise Meitner was studying the beta decay. In the studies of Lise Meitner at that time, it was not only a puzzle about the continuous energy spectrum, the other puzzle was that it was also simultaneously found that there were also electronic lines of a single energy of an electron, which was measured, and that resulted from the interplay between gamma radiation and beta radiation. And depending on what is the gamma ray doing, what's the gamma quantum doing with the electrons of neighboring atoms, or even inside the atom, that resulted on different electrons being ejected from that, and that was observed in the spectrum. And there was the interchange and competition between Cambridge, especially with Charles Drummond Allos. And so since we are here in Cambridge, I wanted to mention this. You can read the final result. We have verified your results completely. It seems to me now that there can be absolutely no doubt that you were completely correct in assuming that beta radiations are primarily inhomogeneous. By that, she means that you have both the continuous and the lines in the electrons. But I do not understand this result at all. Okay, it relates to the next point, namely the issue about Auger electrons. As a follow-up, when you have, since we mentioned that in the morning already, the photoelectric effect in the morning was 1905, when Einstein explained that. When you kick out an electron in an atom, it could be kicked out by a photon, then you have the photoelectric effect, or it could be kicked out by an electron, which you easily also have in all these processes. Then as a follow-up process, you can either have the emission of an X-ray or the transformation of energy to another electron in the outer shells, and that is then called the Auger electron emission. And these lines, these are then distinct electron distinct in their energy. You can measure them. These lines are also participating in the spectrum when you measure the electrons in studying beta decay. And since that was observed, and I think in a paper of 1922, that was described in the study of a bismuth decay, so there is good evidence that Lise Meitner knew about that already. Although Pierre Auger published, I think, the paper in 1924. He had a thorough investigation over the various elements, so he could really also show the dependence of the Auger lines with respect to the atomic number, to the Z. So in that sense, that was more complete, and the understanding was much more thoroughly than in the simple explanation of one beta decay. So it would be very fair if the effect would be named Meitner-Auger or Auger-Meitner whatsoever. To address it only to one scientist would be a little bit misleading as well, but it would be very fair if that could be done. What is Auger spectroscopy good for nowadays? It's a big business. When one is dealing with surface science, when you want to grow certain things on top of very clean crystals, silicon crystals or whatever, or 3,5 crystals in light emitting diodes, etc. You want to really build up structures layer by layer. And you need to check on the purity of the surface of such crystals when you want to grow such crystals, when you want to construct some of these structures. And in order to control that, you actually use the Auger effect. All these nice heavy equipments in the lab, complicated vacuum vessels, you have to go down to 10 to the minus 11 or 10 to the minus 10. If you are better, then would be nicer. In order, all these equipments, they always have one feature added to that, and that is an Auger spectroscopic device in order to make control of the growth of crystals and layers on top of these crystals. So if that would be called Auger-Meitner, it would be very nice. Okay, the other subject, all appearing during her research description and stories about that and history of that, that is, of course, the dealing with transuranium elements. And that is now illustrated often by, since we are in Britain, sailing nation, you have to go sailing and to go to sail to something which is unknown, to discover an island which is not yet really fully understood or not understood, and want to discover a new island of stability. So that was the big thrive about 30 years, 40 years ago. It started with Fermi and with Lise Meitner and Otto Hahn by using neutron capture. And with the neutron capture, it continued then to do, and that was the Joliot-Curie, the couple in Paris, to do nuclear reactions. You do light particle reactions like alpha particles or protons, and you come to the next element in the beyond the uranium. Nowadays, you use heavy ions like lead ions or calcium ions or what have you. And these experiments take place in Berkeley, in Dubna, in Darmstadt, and in Japan as well. And here's the periodic table. Typically, you are used to ending here with your uranium, and anything else is now added in the meantime, up to element 118. Uranium is 92, so we are now at 118. It looks nice and regular, although it's very difficult whether the assignment of the position in such a table is here and there still questionable, so it needs further experiments to do that. To get a little bit of insight here, that is the Meitnerium, element 109. There is no hahnium, to be sure of that. There is no hahnium from 92 to 118. maybe if one goes beyond that to 130, maybe there might be some hahnium coming up as well. The hahnium, I guess, somebody tried to do that, and that is hassium. Yeah. I want just to show the protactinium, which was mentioned, which is actually not a trans-uranium, but below that. Okay, that's more or less it in terms of science, what I wanted to say. Now a few words about the connection leading to the political issue as well. And that is to get the relationship right. Heinz Meitner in 1959 were, so to speak, awarded the name of an institute, which was founded in 1959. The inauguration was done in the presence of the mayor at that time of West Berlin, Willy Brandt, the later Chancellor of the Federal Republic, and you see Lise Meitner there and Otto Hahn there. And the other important point why I actually figured I should do something about, because of my connection to the Free University, was the awarding of the honorary doctor's degree of the Free University in May 1957. But this was only because she refused to actually take part in a celebration which was taking place in 1956 in December, where Max von Laue tried to convince Lise Meitner to come over to Berlin to give a speech to the reopening of the former Kaiser Wilhelm Institute, now the Organic Institute, at that time the Organic Institute of the Free University, Organic Chemistry Institute, and she refused at that time to go there, and so she was awarded the doctor's degree half a year later. And to summarize, something like this is happening during the full semester at the Free University with all the different lectures concerning Lise Meitner. I only want to point out that the final talk will be given concerning Rosalind Franklin, since she was mentioned earlier this morning, and that will be presented by Christiane Nüsslein-Vollhardt, a Nobel Prize winner. And I think it's just a new sculpture in Berlin, and what's nice, Lise Meitner is facing Max Planck, since he was mentioned as well, so I guess I finish with that.
So before we go on to the other two speakers and other aspects of her life, questions? We've still got roving mics. Anyone wants to probe into the physics? There's one here. Archie, so have we got a mic?
Well, thank you for, is this on? Thank you for the science. One of the Val Gibson slides mentioned these two of these key discoveries of Lise Meitner, the recoil and the Auger-Meitner effect. And that was done, well, the second of these certainly around about 1922, I think. I wondered afterwards, of course, this is being said with the benefit of hindsight, whether both of these things might have been useful later on when the fission issue arose in making the chemistry a little bit less necessary. They could have been solved by recoil and Auger spectroscopy. It would certainly be possible today. And she had quite, I was impressed when I looked at the early paper in the Auger work, the precision with which the spectroscopy was done, and they could identify the K shell and the L shell in quite heavy elements. And so they might be able to tell the difference between different elements.
Do you want to comment?
Okay, about the Auger process, the Auger and the X-ray emission, they are competitive. And for low Z elements, the Auger effect is dominating. For hydrogen, you don't have, or hydrogen doesn't burn, but helium. For helium, you don't get photon emission, you get only Auger electrons. And vice versa, in the case of uranium, you only get X-rays coming out and very little Auger. So in order to determine the different elements in the fission, for example, by Auger spectroscopy or X-ray spectroscopy, Auger wouldn't be sensitive enough for that. And concerning the recoil, of course, I guess that was one of her ideas right away when she learned about or explained the fission experiment by Otto Hahn and Fritz Strassmann, that one should look for the energy and should put fissioning uranium onto a surface and to try to measure the energy and also measure the second product, because Otto Hahn only found the barium, and the noble gas element, which is the accompanying element, was missing. And she was successful, and she did that, I guess, in Copenhagen from Stockholm.
We have other questions?
The remark of Alan made about the fact that we're cold, I think in a sense this is an engineering legacy of Lise Meitner, in that at the time the college was designed, people thought nuclear energy was going to solve the energy problems of the world. And the architect, when he built this college, I'm sure put any attempt to insulate the building right at the bottom of any priority list. And I would just ask you, when you go into the hall to eat this evening, to look at all the sources in that hall where you lose heat.
I think it's certainly true that she saw the fission as a route to energy for civilians. So did she get involved with any of that research, or did she keep well away from that even more than from the bomb?
As far as I understand, I'm not a historian, I didn't think she got involved with that at all. But I don't know whether there's any evidence historically about that.
I only could add she was in favor of nuclear energy
Yes.
for peaceful
Yes.
Purposes, yeah.
I mean, that's what she thought would come out of her
When
work.
you were looking around at that time, many physicists believe we will solve the energy problem. We have this horrible bomb, but we have these nuclear Kraftwerk reactors who will solve the problem, and we
Power
will get
plant.
cheap energy.
I mean, certainly in this college, our first master, John Cockcroft, was very much in favour. We've got one of his sons here. But the military kind of took over, as I understand that.
It was this optimism at that
Yeah.
time. You could read, everyone was happy to be part of it.
There's a question here.
Hello, I'd be interested to hear whether you think that there's a strong continuity between the character of Meitner's work and the character of work on similar problems now. I'm asking that partly it would actually have been helpful to think about this in the earlier session. What kind of a scientist was she? What are the particular features of her work that distinguish it? One of the things we've seen is that she's really comprehensive. She often has a broad perspective, and she's aware of the limitations of current understandings. I'd just like to hear a little bit more on the kind of way in which she conducted her work and whether that's similar to the work being done now.
You want to comment, then I will.
Thank you very much for that question. I actually forgot to set a sentence about that. I got the impression from some of the letters, which I read, that she likes very much what I would call a lab-size experiment. An experiment which fits into a laboratory on a table, and that's it. You have seen photographs where she was in front of such apparatus. I got the impression she would have pretty much difficulties in designing experiments on large-scale facilities like CERN or whatever, for example. But of course, she would certainly have adjusted to that. I'm pretty sure. But at least at that time, she didn't like the idea in Stockholm that Manne Siegmann was going for the cyclotron installation, and she wouldn't like to take part of that.
Just to add that science is very different now when you're looking at things like CERN and these large collaborations. It's very difficult just to be a single person working individually, although anybody who is good at experiment as well as theory as well as building things is clearly going to go a long way, and somebody of Lisa's capabilities would indeed be very significant in current day science. Having said that, I mean, we're now going back to an era, I think, where technology is so advanced that we can now consider going back more to tabletop science as well as the big science as well, because you have to cover the full breadth. And I think you mentioned with Katrin, to look at things like neutrino mass, we can start building smaller experiments, and because of our quantum technology, the quantum sensors that we have are such that we now have the sensitivities to try things, new things out. And so smaller experiments are coming on the table as well. But we need all of them to answer all of these big questions. You can't just do it with a single experiment.
But it's also the case, as we heard this morning, that she was interested in interdisciplinarity, the collaboration. So to some extent, you can imagine her fitting into a much larger team than she actually had around her.
Yeah.
So that is consistent. Last word to Alan.
I think you just answered that question, actually.
Okay.
I was just going to ask, I mean, obviously we saw this morning where you had 5 main laboratories around the world that were partly in competition with each other, but partly collaborating with one another. And I was just going to ask how that has developed and how international the subsequent research now is.
Well, in my field, it's a world project, so it's it's totally international. And in the neutrino field as well, there's a lot going on in the US and in Japan, and we're also hosting things at CERN. So it has become recognized that to really make significant advances, you do need to work together without the barriers of politics or anything like that. It is just the only way to make advances in this field. Sorry.
You have the problems of email anyhow. Okay, well, we probably should change tack slightly now and go over to the other half of this panel. If I can pass over to Georgina.
Thank you, Athene. Good afternoon, everyone, and like everybody else, I'd like to thank the organisers of this symposium for inviting me. I feel a little bit of an interloper because I've never done any work on Lise Meitner, but I guess I'm here because I have a bit of a reputation for writing about women in science, largely based on the work that I've done on the life of Dorothy Hodgkin. And if you'll excuse me, what I'd like to do is begin by just making some comparisons between her life and scientific career and that of Lise Meitner. So just to fill you in on a little bit about her story, Dorothy Hodgkin was born in 1910. She died in 1994. And she was an X-ray crystallographer and had a very, very interesting life. I think that was one of the things that drew me to work on her, that she almost spanned the 20th century and so lived through an extraordinary number of political and social and scientific changes, including things that not only the advances that made it possible to solve the structures of complicated biological molecules, but also the education of women, especially the higher education of women, the relationships between East and West, in which she was very much involved, and the various upheavals of peace and war that took place during her life, and the development of international collaboration. And these were all But I have to say that my own motivation for writing a biography of her, which I began just after she died, was a very naive one. I just thought, here is this woman of extraordinary achievement, and if I started chatting to people I knew, saying I was thinking of doing some work on Dorothy Hodgkin, they would, this expression of panic would come over their faces, and some of them would say, did she have something to do with Hodgkin's disease? And the answer is no, by the way. And nobody knew who she was, and it was simply, for me, a matter of putting something right, that she should have a biography. I was astonished she didn't have one by this time, actually, because she was a person of such distinction, and I'll go into what that was a little later. And I just had this naive idea that anybody of that level of distinction, there would be a biography, and there wasn't one, and there wasn't even one underway, and so I put myself forward, and the family very kindly agreed that I could go ahead and do it. And I think now that was a sort of naive justification to think that it should be done just so that she should have the recognition, almost as a sort of out of respect or out of giving her something. But I suppose we'll come to talk about this a bit more later, but the person concerned is dead. So you're not really benefiting them by honouring their memory. You have to think a bit harder about why we need to honour the memories of people like Dorothy Hodgkin and Lise Meitner. But to come to some of the comparisons with her, I was very struck by what was said this morning about how supportive her family, particularly her father, were. And this was something that's very much true of Dorothy. Dorothy Hodgkin was born in 1910, so she's 32 years younger than Lise Meitner. So many of the changes had already taken place. Higher education for women was becoming more common, although careers for women were still not something that was at all normal, certainly scientific careers. But it was very much, she was one of four sisters, and it was very much her father and her mother. I didn't hear much about what Hedwig's role was in Lise's career, and we might talk about that later. But both Dorothy's parents had intellectual interests. I wouldn't have said her mother had a career, but she was intellectually interested in archaeology and botany, and she produced a number of books and publications and became, in fact, the world authority on ancient textiles, simply through her own interests. So she grew up in a family where intellectual interests were absolutely normal, regardless of your gender, and the fact that she wanted to go to Oxford and read chemistry was seen as completely normal, and she was encouraged in that, and I think that was very important. She described herself as having been captured for life by chemistry and by crystals at the age of 10 when she grew crystals in a little class that she attended at the time. And at her secondary school, chemistry was taught. It was a mixed school, but normally the girls did needlework while the boys were doing the chemistry, and she and another girl in her year had to fight to be allowed to join the chemistry class, which she was able to do. Another thing that I think, I'm not going to go into everything that she did because this isn't a meeting about Dorothy Hodgkin, but another thing that I think is extremely important in her career is having supportive male colleagues, particularly people like J.D. Barnard, who was a mentor to her throughout throughout his life, certainly all through, even when she'd become very eminent in her own field, he was somebody she constantly referred back to. And that support was very critical for her to her becoming established. And again, like Lisa, she was recognized in her lifetime for the work that she did. She and Barnard together published the first paper on the X-ray crystallographic analysis of a protein molecule in Nature in 1934. She was still a PhD student at the time, but that paper is regarded as the founding paper of protein crystallography, which is still an enormously important field in the world. She was admitted to the Royal Society at the age of 36, which is still pretty young to get in. It was only the third year that they'd admitted women at all. So I think that makes her, roughly speaking, the fifth woman to be admitted to the Royal Society. I've just written down Geary Schmitt because I saw that, I think it was Annette who mentioned his name. Tell me, did he go to Oxford as a refugee? Okay, so he worked in her lab. So here's a connection that Geary Schmitt worked both with Lise Meitner and with Dorothy Hodgkin before he subsequently moved to Israel and made the rest of his career in Israel. She was also, this is something you have to worry about a bit as a biographer, she told another person who wanted to write a biography that she was wary of attempts on her life. So she wasn't keen on the idea of biography. Somebody had started one, but she kind of put him off with the excuse that she was going to write her own memoirs, which she never got round to doing. So I'm not confident that she would have liked what I did, but fortunately her family were quite happy. And similarly, she wasn't wild about being the constant attention she had from the press. I think she was more, it sounds as if she was more receptive than Lise Meitner was, and there are a number of features in women's magazines and so on of her. But she got to the point where if she was busy working, even after she was technically retired, she was still working. And if the phone went and it was yet another journalist, she'd say, "It's very boring if you always ask the same people." There was a reason why they always asked the same people. And of course, the question of her, this word humanity that we've heard used in relation to Lise Meitner and as part of her epitaph. Dorothy Hodgkin was politically engaged and active. She was very much on the left. She had friends in Russia, she had friends in China. Her husband was a communist, her mentor, had been a communist. And she was extremely concerned to promote peaceful relations between East and West. She was very much opposed to war. She campaigned against the Vietnam War, for example. And she was extremely engaged with encouraging international scientists, particularly scientists from developing countries, to come and work in her laboratory. So she wasn't entirely in the lab focused on what was going on under her equipment. She was very much somebody who had a world view and wanted the world to be a better place and to do what she could to make it a better place. And I've come at the end to the kind of obvious thing from the picture that I've put up. The big difference between her and Lise Meitner is that she did win a Nobel Prize. She was also nominated a couple of times in the 1950s, unsuccessfully. But it was actually after Max Perutz won the prize for physiology or medicine, for chemistry in 1962, for solving the structure of hemoglobin. So he actually got the first protein structure. And he subsequently nominated her again, and she won the prize as the sole winner in 1964. And so I'm very much agree with everything that was said this morning about the Nobel Prize and how it's seen as everything when actually to the individual scientist there are many, many other forms of recognition within your peers. I think the thing about the Nobel Prize is that it's something, it gets into the papers in a way that the awards that are given within science simply don't get that level of recognition. And it's probably just because it's such a lot of money. There are a couple of other prizes that have come up. Sorry?
And the myth.
Yes, the myth, yes. But I think it probably goes with the money. And people get very starry-eyed about very large sums of money. And they think this, but they do imagine that it turns you into a kind of sage who can pronounce on absolutely anything. And I'm going to change gear quite a bit now and talk about this whole question of fame, because we talk about it, I think it was Ruth this morning who used the phrase written out of history, literally written out of history. And that happens to a lot of women. It's become a phrase that's used in talking about women scientists, especially those who appear not to have had the degree of recognition that they deserve, that they were written out of history. And I wanted to see if I could do some kind of analysis of how famous these women that we're talking about are. And I thought I'll just do a cheap and dirty study myself. I'll see how many Google hits they've got. So Lise Meitner has over 2 million Google hits currently. And Dorothy Hodgkin only has 763,000. So winning a Nobel Prize doesn't necessarily get you more Google hits. I don't mean that makes you more famous. I realize this is an extremely dodgy way of measuring anything, but I just thought I'd do a quick way. And then I thought, well, because one of the things that has happened, particularly since the 80s, I think, with women, is that because they've been underrepresented in the past, there's been a tremendous effort to raise their profiles, and that number for Lisa looks pretty good. So I thought, well, is she now better known by Google than Otto Hahn? Oh, sorry, I did Rosalind Franklin next. I did Rosalind Franklin next, and she comes out at 12 million. And I think we all know that that's because she has been represented with some justification, possibly not as much as there has been, but as somebody who was really badly treated by others making use of her data and her not being recognised at that time. So she's got this kind of victim status, which I'm sure she would have hated, but I think that probably accounts for that reason. But then I thought I'd look at Otto, and he comes out at 34 million Google hits. So then I discovered that there is actually a slightly more scientific approach to this that we could look at. And this is a study that was done at MIT a couple of years ago, called Pantheon. And the people, this is the part from their webpage, and the reference is there. They ask you to give the reference if you talk about it. And what they've done is taken people from all walks of life and create a database. And the basis of it, you get into the database if you have at least 25 separate language editions on Wikipedia, because they're trying to get a measure of global fame, not just, if you just use Google, I think it's very skewed towards American or certainly English-speaking pages, but this is meant to be a measure of global fame. And then you can choose different domains. So I put science and technology in, and you can also choose time periods. So this is everybody born since 1850, and the top 5 there, Albert Einstein, you probably can't read it, it's Albert Einstein, Sigmund Freud, Max Weber, I don't know how you pronounce him, Marie Curie, and John Maynard Keynes. They include economists and mathematicians in science and technology. I can't do anything about that. So you've got Marie Curie there at number 4, which is not bad, really, and it's pretty obvious that Einstein's going to be number 1. And Lise Meitner is the second woman in the list at number 111. So it's quite a long drop before you get to the next woman after Marie Curie. And Dorothy Hodgkin comes in at 404. So again, Lise Meitner is well ahead of Dorothy Hodgkin. Rosalind Franklin drops all the way down to 656. And I'm not sure whether they do say that this is a manually verified data set, and whether something to do with their manual verification accounts for that difference between what you get in the Google hits and what you get in the... Oh, I'm sorry. The ranking is you get into it by having at least 25 pages, but then they count the number of page views. That's what determines the ranking, and a few other things as well. I mean, it's how many more, because some people have got up to 40-odd different language pages. So that all feeds into the ranking. You can read the methodology for yourselves if you're geeky enough. So then I put Otto Hahn in again. He comes up at number 53, and all the women are lower, apart from Marie Curie. And Rosalind, and then I put Max, that's right, I put Max Perutz in because he was the nearest equivalent to Dorothy Hodgkin I could think of. He spent most of his career in the UK. He was an X-ray crystallographer. He was almost her exact contemporary in terms of his age, and he also won a Nobel Prize. But he comes out slightly lower than she does. But I think this bit I put at the bottom is the chastening thing. So this... If you use these criteria in this database, you come up with 962 biographies on Wikipedia in the domain of science and technology born after 1850 who meet the criterion of at least 25 Wikipedia language editions, of which only 36 are women, which is slightly under 4% of the total. I then, just out of curiosity, ran this again on people born since 1950, expecting to see a change. There is a change. The percentage of women is slightly under 3%, not slightly under 4%. But what does this all mean? I have no idea what this means. What does it mean that people are searching for people on websites. Is that fame? Is that what matters? Clearly, to a scientist, that's not what matters. To a scientist, what matters is your published record and your reputation among your scientific colleagues. But I think one of the reasons we're here today is because we are concerned that names like Dorothy Hodgkin and Lise Meitner are not particularly well known by the general public, and we're concerned about that. So I think the next questions to ask are why are we concerned about that? Who does control these cultural legacies of people like Lise Meitner and other women scientists? And why should we remember? What are we trying to achieve by raising their profiles among the general public? And what is the impact of that raising of the profile? And I've put these as questions. I don't really have answers. One impact that kind of comes back to me and that I'm aware of and rather encouraged by is that I periodically get emails from schoolgirls, particularly in America, because they have a big history prize where they have to do a project for a history prize. And I get asked to do interviews with them by email for their project on Dorothy Hodgkin. So they know something about Dorothy Hodgkin, and they're doing their history project on them. I've even had a group of high school girls in South Korea who wanted to translate my book. And so these names are filtering down to the people we really care about meeting, who are these girls who we would like to encourage to go into scientific careers. So I think although those numbers were a bit, those percentages were a bit depressing, something is filtering through, and it's worth doing. And I hope we'll have the opportunity to discuss that a bit more. And finally, I've just got this, I just shoved this in at lunchtime, but I remembered that there's a rather beautiful photograph of Dorothy Hodgkin that was taken by Lotte Meitner Graf. So that's another connection between the two families. And that's the photograph. It was commissioned, I think, when she was, it says Royal Society on my note. She looks too old for it to have been when she was admitted as a fellow, but I think it was when she got the Royal Society's Wolfson Professorship in 1960. That picture was commissioned. Thank you very much indeed.
Thank you very much. Many questions to ponder there about the legacy and the importance of women culturally in inspiring the next generation. We'll take questions after the next talk. So over to Tanja, and we should have time for some questions after that.
Yeah, so thank you very much. What I'd like to do in the next few minutes is to share some considerations of Lise Meitner as a role model for women in science. When it comes to the legacy of Lise Meitner, at least in her country of origin, Austria, her installation as a role model for women in science has become predominant only in recent years. For example, in 2008 there has been named the hugest lecture hall at the University of Vienna, the Lise Meitner Hörsaal. Or in 2015 there has been a sculpture at the main building in the university, in the courtyard. When you entrance the library of the Zentralbibliothek für Physik, also in Boltzmanngasse, you find there posters from Lise Meitner everywhere, even though there are the literary remainings of Schrödinger and a few other people. There are much less posters from them. Also the National Funding Agency, FWF, has named a funding scheme for postdocs after Lise Meitner. So it is a matter of fact that nowadays Lise Meitner is seen as a role model for women in science. But how did Lise Meitner herself feel about that as a role model for women in science? When she was already in her mid-80s, Thomas Kuhn conducted an interview with her. We've heard about it in the morning. And it's revealing that when Kuhn asked Meitner what her problems she had as a woman in science, she can't help but go into raptures about Max Planck, Emil Fischer, and all the other top male researchers who supported her in building up her career. And I think the essence of her answer can be found in one sentence where she says, I quote her, "I had such nice colleagues that it is impossible for me to say that things were difficult for me." Interestingly, Meitner changed her opinion concerning women in science quite radically over the years. While her career was going just fine in Berlin, she hardly supported other female scientists. On the contrary, she often had her reservations. And it is interesting to see how she complained about two female students, calling them femini generis, who cause her headache, in a letter to her friend Elisabeth Schiemann, another female academic. Annette has shown the cover of, it's reprinted in a book by Jost Lemrich, the letter exchange of Meitner and Schiemann. And also in a letter to Otto Hahn from 1930, Meitner wrote quite frankly, "In general, I do have many concerns about female students." Obviously, by that time, she would probably have refused to be installed as a role model for other female scientists. She rather felt as the exception than a pioneer for female physicists. And it is only in her 50s that Lise Meitner came to realize that not all talented female researchers received as much support as she herself did. At that time, she questioned the reasons of a colleague who criticized a female student and asked him if he would also criticize this student if she was a man. And it was in those last years of Meitner in Berlin that she developed what I would call a very subtle feminist conviction. Her awareness of gender issues was reinforced once she lived in Sweden. Certainly in Scandinavian societies, equality was much more developed than in Germany at that time. In Stockholm and also during her trips to the US, Meitner appeared as a lecturer at events from women's organizations, and publicly as well as privately, she reflected on her role as a woman in science. Referring to the subtitle of this symposium here, celebrating a scientist who never lost her humanity, I'd like to stress that one of the aspects I personally really admire about Lise Meitner is that she did not stick to her opinions, but that she was ready to rethink her positions. One example for that is her early enthusiasm for the First World War, which gave way to an aversion in the Second World War. And this change of thinking also is true for her stance on female scientists. To illustrate how Meitner herself thought about her change of thinking concerning gender equality in general and women in science in particular, I'd like to give you a quote from a radio talk she gave in 1953. There she said, "As a young woman, I didn't know much about the women's movement. In particular, I was not aware of its contribution to very different issues ranging from individual to social life. Of course, I had read a few texts on the role of women in science, but in society, but I did not believe that books like On the Physiological Idiocy of Women by Paul Julius Möbius or Are Women Humans by Max Funke had to be taken seriously and had to be refuted. Only later I came to realize how wrong my opinion had been, and that every woman who is working in the academic field should be grateful to those women who have fought for equality." So even though Lise Meitner hardly ever felt discriminated, I mean, she did a few times, but not so often, as a woman in science, there are several occasions in which her contributions have been neglected. The Nobel Prize has also popped up a couple of times before. I'd like to draw your attention once more to the question of the Nobel Prize as a symbol for public outreach of scientists. So in this decision, as we've also heard before, the possibility cannot be ruled out that one of the aspects that Meitner was ignored was that she was a woman. Altogether, the rate of female physics laureates is rather low, so by now we have 3 laureates for physics. The last one, Donna Strickland, just received the prize a couple of weeks ago, actually. And along the way, many other women have been missed out. In a nomination letter by Max Born from 1964 for Lise Meitner, he mentions that previously I quote him, he had become aware that there seemed little chance for the award to the prize to a woman. Evidently Meitner was not the only one left out. A famous example is Miss Wu over here. She conducted the so-called Wu experiment, which probably many of you know, which contradicted the hypothetical law of conservation of parity. 2 of her male colleagues got the prize, and she was left out. Another famous case, which might be well known here, is of Jocelyn Bell Burnell. During her PhD here in Cambridge, she pushed towards the discovery of the first radio pulsars. So that's Bell Burnell. But also 2 male colleagues received the prize. She was the junior partner, and also Vera Rubin provided data that gave the first evidence for dark matter, also a discovery not honored with the Nobel Prize. It was only last year that the bodies in Stockholm that award the prize have publicly recognized that there are more people from underrepresented groups who deserve the prize than receive it. And for this year's prize, now 2019, nominators are recommended to consider diversity in gender, geography, and topic in their nominations. In October, we shall see if finally women or other researchers from underrepresented groups will be decorated with this most prestigious of all scientific prizes. And with this cautiously optimistic outlook, I'd like to come to an end, and thank you for your attention. Thank you.
Thank you very much. So, yes, more about Nobel Prize winners. Right, you had a question already, so.
This is really more an observation about the number of Google hits for Lise Meitner and so on. Could one possible explanation for this be that they didn't, the ones that had the higher hits didn't win the Nobel Prize? And in this light, it would be interesting to see how many hits Jocelyn Bell got.
Yes, one can go on playing this game for hours. It's a tremendous time waster if you look it up. Yes, I think I got contradictory results because, as you say, Lise Meitner got the higher hits, which could account for which your explanation could be correct, as did Rosalind Franklin. But then looking at the other data, the Wikipedia data, which is more comprehensive, Lise Meitner again came higher up, but Rosalind Franklin came much further down. So I was somewhat thrown by that, and I'm glad I'm not having to write a paper about it and explain it. But I think you're right that certainly.
It's the controversy.
I think if a man, you could challenge me on this, if a man had done the work that Rosalind Franklin did, and his work being used the way Watson and Crick used it, would he be as high profile now as Rosalind Franklin is? And there could well be many other men out there who didn't get Nobel Prizes but who might have done. And I would imagine that they haven't had quite such large campaigns of people raising their profile and trying to get them the recognition that they deserve. So yes, I think there is an effect of more recent feminist historians and educators raising the profile, which will have pushed them up.
More questions? Or perhaps I can ask one. I'll come back to you in a moment, Tim. So we've been talking about the Nobel Prize, and there's always this chatter about women being discriminated against. Now, I happen to have one, as have two honorary fellows in this college, the L'Oréal UNESCO Laureate for Europe for Women in Science. And somehow I suspect that both Meitner and Hodgkin would have been horrified by the idea of prizes for women, which I entirely understand. But on the other hand, if we are going to try and percolate information out to the general public, I'm not sure that we don't still need them. I mean, it is a fact that when I won the prize, suddenly the BBC wanted to talk to me. You know, I got onto Woman's Hour, I got onto Desert Island Disc, which some people say is my main claim to fame. But I mean, it is a way of getting the idea that female scientists are out there to the general public. So what's your view about prizes for women only?
I think you're right that they serve a purpose, but I mean, I'm sure you know, I'm sure you have come across female colleagues or women in other areas of science who look askance at you for doing as much campaigning as you do on behalf of women in science. Because I mean, I certainly know a number of women who are very, very senior, but who don't like sitting on panels to talk about women in science and want to be regarded as scientists and not as women. And that's what they'll say. I'm a scientist, I don't want to be regarded as a woman. And they are not necessarily particularly supportive to younger female colleagues, some of them. Some of them are, but they try to do it in a very low-key way. Because there is a fear of special treatment, yes. Which is exactly the same as positive discrimination in areas of race and all these other things. Yeah, I mean, there's a story from Max Perutz's life where he employed a black woman researcher at a time, I think she came from California, at a time when the only fellowship that was available to her was a fellowship for black women students. And she really didn't want to take that fellowship. And so for Max to offer her a job in his lab, just because he wanted her to come and work in his lab, she wrote a wonderful letter of thanks. So that it is a bit double-edged.
It is very double-edged.
But from the point of view of raising the profile, and that's something if you'll excuse me just saying this as quickly as I can, because it's something I meant to say in my talk and I forgot. I think we have a problem not so much about being women, but about being scientists, because the activity of science itself requires no audience. So if scientists just get on and do their science and publish their papers in scientific journals, they may be very well known by their scientific colleagues, but they will never get into the public eye, particularly if they work in areas that aren't very, aren't going to make headlines themselves. Scientists only become celebrities if they do celebrity things like presenting television programs or going on desert island discs or writing popular books or talking about God. doing your science as a scientist will never make you famous unless you're, and then you've got cases like Stephen Hawking, who's probably more famous for being disabled than for being a brilliant expert on black holes. I don't know. It's not.
Well, he was certainly a role model for many people. And I first found out what celebrity really looked like when he came to the college for an event about disability. And he came to the dinner and he was going to give his speech, and the entire hall, I mean, all the students that come, the entire hall stood up with their phones to take a picture of him giving this speech, and I've never seen anything like it. And you realise just how much he was an icon. And in some ways that is fantastic, and he played to that, whereas not everyone does. He used that to get the word out there, which is important. Sorry, I don't want to hog it. Tim, is there a mic?
This follows on from both those topics. This kind of science, and I'm coming in from the arts, literature, this kind of science in my field is regarded as modernist science, and it goes together with modernist art, and the revolution in the arts, which is called modernism. One of the principles of that revolution in the arts is that the name doesn't matter, and the gender doesn't matter, and you call yourself T.S. Eliot because that conceals your gender or whoever you are. It's impersonal, and the biographies are rejected because the biographical approach to whatever you've written or whatever you've discovered or whatever theory you've propounded is reductive. It's not about you. It's about nature. It's about culture. It's about the world. And that's a really valuable standard, which far beyond gender, and I would, or colour, and all the other divisions that we live with. So I just thought this was part of the ideal of, especially science, and we in the arts owe that high moral ideal of impersonality to the scientists in the first place.
I feel Tanja should have a chance to say something to you, but I've got things I want to say as well.
Yeah, well, thanks for your comment. I see that point. I think it's also important to keep in mind that, of course, the science cannot be separated from the scientists entirely. And it's also for historians of science important to understand what was the biographical background, etc., political, and also gender plays a role in that. So, yeah, of course, it's just one aspect, but, yeah, not everything to focus on that quality.
Yes, I think that's true. I wrote down, again, it was from something that was said this morning. Somebody said something about thinking that the science rather than the people was what was important. And again, you get that. I mean, scientific biography has gone through various cycles. Traditional scientific biography tended to be very hagiographic. It was written usually by the wives or the junior colleagues of scientists in a very kind of adulatory way. And certainly the idea, you're absolutely right, that the science, that the person, the individual is irrelevant to the science because the science, DNA would have been discovered, the atom would have been split, all these things would have happened, somebody else would have done it if that person hadn't done it, and therefore that person is unimportant. But my perspective as a biographer is that science is an activity engaged in by humans, and the circumstances under which those humans engage in that activity is of enormous interest. And I think in and of itself, it's of interest to historians. I think if we want future generations to be interested in it, then you need them not just to be interested in the abstract intellectual history of these ideas, but how these people came to be involved in the areas that they are. And personally, I mean, one of my favourite bits of reading are the autobiographies of Nobel Prize winners, which if you go on the Nobel website, they're all invited to write their autobiographies, and particularly the bits about their childhood. I mean, the number of them who've blown fingers off in garden sheds. I mean, and they often talk about how just from an early age, they were seized by a desire to understand, and coming from a very wide range of different social backgrounds, but being able to keep that thirst for knowledge and take it through their scientific careers. So I think to write about history of science as if it is a kind of arid succession of intellectual advances rather than an activity engaged in by humans in society. Particularly, again, a thing I forgot to say, X-ray crystallography is a very collaborative field. You can't do it by yourself. You need maths, you need physics, you need chemistry. If you're doing protein crystallography, you need biology. You never find one person who's got all the necessary skills. And so you have to work in teams. And it's a very, very social activity. And usually also involving a lot of sharing, things like sharing software. It's very different from the rather stereotyped view of lone geniuses battling away in garrets.
Ian.
I'm going to make the point, which relates back to your Google and Wiki searches, that do people find the subject first and then find the person, or do they find the person first and that relates to the subject? In science, you often will look at the subject first and then you find out who it was that was behind it. So that could skew the statistics in that. Whereas literature, you find the book first or the author. Anyway.
Yes, that's a good point.
Patricia.
I think there's quite a big counter-example to the example you just gave of T.S. Eliot. If you think about somebody like Isaac Newton, I would bet that you only know one thing about him, that he sat under an apple tree, and I imagine, I would challenge whether you could actually give the famous formula to do with gravity. And I think part of the thing of Isaac Newton was that by making him famous, his followers helped to make science itself famous and very important. So I think you're fundamentally wrong to say that the sciences have led the way in not having individual heroes. I think on the contrary, science has just as many role models and heroes as the arts and literature.
There's a comment over there.
I think I can bring some of these themes back to some of the reasons that we're talking about Nobel Prizes in the way that we are, by reflecting on the history of the Nobel Prizes and the particular importance that Marie Curie played in them becoming famous. And that is that the Nobel Prizes had to earn their place, their cultural place. And the initial prizes didn't attain much media attention. And the award to Marie Curie was enormously important in making the prizes well known. That's especially the science prizes. The literature prize had become actually a bit more famous early on, I think, and maybe the Peace Prize. But the reason that she got the prize is entirely due to the work of her husband, because the Nobel Committee initially wanted to award him and Becquerel the prize. And he wrote to them and he said that he would not accept a prize on his own. He would only accept it if it was also awarded jointly with Marie Curie. And there's a very important feature of the practice that he and Marie Curie carried out, which is that in every paper that they wrote, either singly or in collaboration, they always specified very clearly what part of the work each was responsible for. It was very important, therefore, that they signed their papers M and P Curie. And they gave the initials, both of their initials. Historians have looked at the work of Rutherford in this period and found that he read papers by M and P Curie and cited P Curie, not M Curie. So they had to work quite hard to get recognition for their specific contributions, and they did so by including their names. But they would also have supported the sense in which science should be independent of that. And it was really moving in a way to hear Val describe her giving science lectures in which names were irrelevant. And I'm wondering how one reconciles that sense of the aim for a gender-free science and the importance of recognizing clearly the contributions of specific individuals and specific groups and sometimes even specific classes of people. Perhaps we can't solve that. perhaps we have to allow the tensions to exist.
Do either of you want to comment on that? Or indeed Val?
Yes.
I just actually want to come back to Athene's question whether we should have awards for women. I'd take any award. And the reason is, I would, on the condition that it would actually help more women scientists to come into the field and to expose more women to the great research that women scientists do. And I think there's a great pressure actually on women scientists these days to actually give their prizes away and do things for the next generation. And I don't know, maybe it's a question to the historians as well, that we've got instances where Lise Meitner was given some of Otto's Nobel Prize and she gave it away, in circumstances where she probably really needed it. We have Jocelyn Bell-Burnell who gets the Breakthrough Prize and she gives it all away for into the Institute of Physics to educate the next generation of women scientists. I don't know of any man who's won the Nobel Prize who has done that. And I think, there's such pressure on women scientists these days to actually go out there and do more than I think is really necessary.
Can I just add one thing there? There is one man who gave his prize away. That's Albert Einstein, who gave it to his divorced wife. Which reflects another
not the prize, the money.
Yes.
Only the money, not the prize.
Well, at this point, I'm sorry, I'm going to break things off. There's a tea break. Please continue your discussions over tea. There is clearly plenty still to discuss. Thank you all to the wonderful panel.